Use of epoxides in synthesis offers a really powerful tool. There are two recurring themes regarding the use of epoxides that I want to emphasize. First, the ring opening reactions of epoxides place functional groups on adjacent carbons. One of those functional groups will be a hydroxyl group, either on this carbon or this one. The other functional group will be the nucleophile that added during ring opening. And I should remind you that we're talking about one of these products or the other, that these are regioselective reactions. The second aspect of epoxide chemistry that we need to pay special attention to is stereochemistry. We know that because these ring opening reactions are stereospecific, there will be a specific relationship between the nucleophile and the hydroxyl group that is dictated by whatever stereochemistry the reactant had. Keeping these two themes in mind, let's look at a few examples of the use of epoxides in synthesis. When we start with an acyclic epoxide like this, we can open that ring to put a nucleophile on the terminal carbon. We'll use the conditions without acid catalysis to be sure that the nucleophile adds to the less substituted carbon. And we know that sodium cyanide is a great source of a nucleophile. So here we have it. We have two adjacent carbons with two functional groups. We get the idea that it came from an epoxide because one of them is a hydroxyl group and the other is a good nucleophile. But wait, we could think of other relevant things regarding synthesis. For example, this cyanohydrin can be oxidized, and then we would have a cyanide group next to a carbonyl. Still, two adjacent carbons with functionality. And we know that PCC is a good mild oxidant to oxidize secondary hydroxyls to ketones. And to extend our thinking about synthesis, we might wonder where this epoxide could come from. Well, it would come directly from an alkene. And we know that peracid is a good reagent for transforming alkenes into epoxides. So here's a three-step synthetic sequence where we transform an alkene, a molecule that we'd like to have two functional groups on, into an epoxide that lets us introduce the adjacent functionality and then oxidize the alcohol into a ketone. This cyanoketone is our target. We start with a compound that has the right number of carbon atoms, this alkene, and we use chemistry that puts the functional groups on adjacent carbons. Let's look at another example. I'm thinking about starting with the same epoxide, only now we use acid-catalyzed ring opening to add the nucleophile to the more substituted carbon. If we use methanol and acid, you see that we make a hydroxy ether. And as before, one of the things we might think of doing with this compound is oxidizing it. This methoxy alcohol could be easily oxidized to the carboxylic acid with the methoxy group on the adjacent carbon. We'll have to use stronger conditions for this oxidation. And again, like before, we might wonder where we would get this epoxide, and of course it would be from the same alkene we looked at before, with epoxidation using peracid. So this time, here's our target. It has two adjacent functional groups. That's a key for epoxides. One of the functional groups comes from a nucleophile. That's the methoxy group. The other one comes from an adjacent hydroxy group by oxidation. To start our synthesis, we'll pick an alkene that has the right number of carbon atoms. When a cyclic compound has the epoxide functionality, it's easy to see the stereochemistry. We've seen that treatment of an epoxide with HCl gives acid-catalyzed ring opening with inversion of stereochemistry where the nucleophile adds. So the hydroxyl group and the chlorine have trans stereochemistry on this ring. When you think about other things you could do with this, one of these is to replace a hydroxyl group with chlorine. We know a reaction that does that stereospecifically with inversion. So this is a way to make the cis-dichlorocyclopentane, because treatment of alcohols with thionyl chloride replaces the hydroxyl group with chlorine with inversion of configuration. And finally, again, when we think about how we could make this epoxide that we want, using an alkene comes immediately to mind, again with peracid. So this time we've made a target that has adjacent functional groups that are cis, the two chlorine atoms. Because after we open the epoxide, we have inversion of configuration. So in a three-step synthetic approach, we can transform that cyclopentene into cis 1,2-dichloryl cyclopentane. The same stereochemical thinking applies for acyclic compounds. It's a little harder to see, so you need to be careful how you write it. Take a look. Epoxides have well-defined stereochemistry, like other ring compounds. Just to be sure we're all on the same page, I'm going to write CH3 here and CH3 here. And when this epoxide is treated with a good nucleophile in a protic solvent, that nucleophile is going to add to the less substituted carbon. This has fewer alkyl groups, so the nucleophile adds to the less substituted carbon. And again, the same theme applies. We have functional groups on adjacent carbons, the hydroxyl group and the azide group on the adjacent carbon. And the stereochemistry of this product has been dictated by the stereochemistry of the reactant. The stereochemistry at the carbon, where the carbon-oxygen bond remained intact, is unchanged. We have the ethyl group back and the methyl group forward. The stereochemistry at the carbon, where the carbon-oxygen bond broke and the nucleophile added, is inverted, as we see here. So even in acyclic cases, when we look carefully, we see that using epoxides is a great way to control stereochemistry and make compounds that have adjacent functional groups. It's a common theme for use of epoxides in organic synthesis.